Hello all, a very good evening. Welcome back to my YouTube channel, All About VLSI. Hope you're all doing good. And I think my voice is also audible. Can anyone confirm me whether my voice is audible? I hope my voice is audible and my screen is also visible. So welcome to this course on analog electronic circuits. So in this session we are going to start with this particular subject. This is a free course, and yeah, so we will start our session. So in this session we will just start with the basics of semiconductors. What are meant by conductors, semiconductors and insulators. We will discuss about that. Okay. Yeah, so this is the day one of this particular subject, and please do subscribe to my YouTube channel All About VLSI, and do like and share with your fellow VLSI aspirants so that they can also get some help in this subject, right? Yeah. So let us start with the discussion of conductors, semiconductors, and insulators. Basically, what is mean by conductor? Okay, from our childhood we are discussing about what are conductors, and we were studying about these conductors from a very long time, right? So what is meant by conductors? A simple definition: conductors are materials that allows electric charges, typically electrons, to flow through them easily. So these are conductors. So this is the definition of conductors which we were studying from our childhood, right? So conductors are basically the materials which allow the electric charges or the electrons to flow through them easily. Okay, so the movement of electrons is easier in this conductors, right? Next, coming to the properties of conductors. What are the properties of conductors? So basically those are the conductors are high those conductors have high conductive nature. Okay, what is meant by this high conductive nature? They have large number of free electrons that can move freely, which is why they carry current efficiently. Okay, so due to this, current flow through these conductors is large compared to insulators and semiconductors. And low resistivity. So due to this low resistive nature, that is the opposition of electric current, and so these conductors have low resistivity. So basically the resistance is low in these conductors, so the current is high. So this we were discussing from our intermediate or 10th class, like that we were discussing these concepts. Okay, these are just basic concepts what are meant by these conductors. Next, coming to insulators. Insulators are materials that do not allow electric charges to flow through them easily. Okay, so insulators are the materials which do not allow any current to flow through them, or they do not allow any electrons or electric charge to flow through them. Those are known as insulators, right? What are the examples of insulators? We already know the examples for insulators are wood, plastic. Okay, those are the examples of insulators. And coming to the examples of examples of conductors are like iron and copper. Okay, yeah. Next, what are all the properties of these insulators? They are very high resistive in nature. Okay, so insulators strongly oppose the flow of electric current, and due to that they have a very low conductivity. Okay, next, coming to semiconductors. So these are the core for our subject VLSI. So semiconductors are the core for our VLSI. What are meant by these semiconductors? Semiconductors are the materials that have conductivity between that of conductors and insulators. So the conductivity of semiconductors is between the conductivity of conductors and insulators. So their conductivity can be altered by adding impurities. Okay, so adding of impurities to this semiconductors is also known as doping. Okay, so due to this doping only we are going to achieve the conductivity in this semiconductors, right? So the adding of impurities to alter the conductivity is known as doping, or by applying the electric field. Okay, so by applying the electric field or by the process of doping, we are going to alter the conductivity of a particular semiconductor. Okay, so this is how we are going to alter or change the conductivity of a semiconductor. What are all the properties of semiconductors? So in case of conductors, the conductivity was high, and in the case of insulators the conductivity was low, whereas in the case of semiconductors the conductivity is variable. Okay, so the conductivity changes in this semiconductors. It depends upon the doping as well as temperature and electric field. So these three factors play an important role in the conductivity of a semiconductor. Okay, and band structure. So they have a very small energy band gap between the valence band and conduction band, allowing them to conduct electricity when energized. Okay, so these are the properties of semiconductors. And example for semiconductors, we already know silicon. Silicon is mainly used in the case of VLSI industry, right? And germanium and gallium arsenide. Okay, so these are the examples for our semiconductors. And what are all the uses in electronics? So semiconductors are the backbone of electronic devices like diodes, transistors, and integrated circuit ICs. Silicon, for example, is a primary material used in modern electronics. So these are the use cases of semiconductors in electronics, right? Next. And this is a brief summary about the all the type of conductors, semiconductors, and insulators with their properties. So basically the conductivity of conductors is high, whereas the semiconductor is moderate or variable, and insulators is very low. So insulators have low conductivity, whereas the resistive nature of conductors is low, and semiconductors is moderate, and insulators is high. And coming to electrons, so conductors have more number of free electrons, and semiconductors have controlled free electrons, and insulators almost don't have any free electrons. And movement of these electrons in these conductors are free, whereas in case of in semiconductors the movement is by doping. Okay, so if we perform this doping only, we will get some electrons. And here also in insulators also conductivity is achieved by only electrons. Only in the case of semiconductors the conductivity is achieved by help of doping. Okay, so this is a brief summary about conductors, semiconductors, and insulators. Now let's directly jump into PN junction diode. Okay, so let us start with the discussion of what is meant by PN junction. Okay, so a PN junction is formed by joining two type of semiconductor materials. So a PN junction is formed by joining two type of materials. One is P type and another is N type. Okay, so I will draw it here. So let us say this is our semiconductor. You can take an example of silicon. So this is our semiconductor silicon. This is a semiconductor bar. Okay, so how to form a PN junction? So basically first we need to form a p-type material. Okay, we need to form a p-type material or p-type region. Okay, so how to form a p-type material or p-type region? So we will basically perform the process of doping. So we are going to perform a process called doping. So what we are going to do in this doping? So we are basically going to dope a p-type material which has a abundance of holes. So basically we are going to dope a material called boron. Okay, so we are going to use this material boron and we are going to dope this with silicon. Okay, so boron will have basically three valence electrons. There will be one empty valence shell. Okay, so that will create hole. Okay, so basically this is a boron atom and it has 3 electrons and 1 valence electron. So this is nothing but a hole and this is nothing but a electron. So if it what happens in this doping is basically silicon atoms are arranged in this manner in this particular bar. So basically this silicon atom is replaced by this boron atom. So finally what happens, this silicon atom will be replaced by one boron atom like this. So this boron atom will have 3 electrons with it and 1 valence electron. Okay, so this valence electron is nothing but a hole. Okay, so like this, we are going to dope this particular silicon or semiconductor bar with help of this boron. So we are going to create like this process. By following this process, we are going to form a p-type material. Okay, so like this, we are going to form a p-type material. So here it is what it is written. So a p-type material has an abundance of holes. So a p-type material will have more number of holes. Remember this. So a p-type material will have a more number of holes. Okay, how we are going to create a p-type material? Just now we have seen. Okay, so a p-type material will have a lot number of holes, positively charged carriers, created by adding trivalent impurities. Okay, creating by adding trivalent impurities such as boron. Next, whereas in case of n-type semiconductors, n-type material which has an abundance of free electrons. Okay, in case of p-type, it has abundance of holes, that is majority of holes, whereas in the case of n-type, it has more number of free electrons, created by adding pentavalent impurities such as phosphorus. Okay, in the previous case, we have created p-type material, right, by adding boron. Same like that, we are going to add this phosphorus atom. Okay, we are going to add, or we are going to dope this silicon with our phosphorus. So what happens? So let's say this is our silicon bar, only silicon. So when we add boron by the process of doping, so boron atoms will replace the silicon atoms. The boron atom will replace the silicon atom bond. So like this, a boron will replace the silicon atom. So boron will actually have, so here we can see here, so boron is a pentavalent impurity. So it will have one extra electron with it. Okay, not boron, phosphorus. Phosphorus will have extra valence electron with it. Okay, so all the 4 electrons will involve in this bond with the silicon atoms, and 1 electron will be left here. Unlike the boron atom which has 1 extra hole, phosphorus atom will have 1 extra electron with it. Okay, so phosphorus atom, due to this extra electron which is present, so by doping this boron with this silicon, we will form a n-type material. We are going to form a n-type material. Okay, so this is how we are going to form p-type material and n-type material by the process of doping. Okay, what are we going to do? We are basically going to perform a process called doping, and we are going to create n-type materials as well as p-type materials. Okay, so let us once again see this. So p-type materials has an abundance of holes, which means we have a majority of holes, positively charged carriers, created by adding trivalent impurities. So we are basically adding the impurities to create a p-type material, as well as we are also going to create a n-type material which is having an abundance of free electrons. Okay, here we have free electrons. So we are consider the example of phosphorus, and we have seen how we are going to create a n-type material. So this is how we are going to create. So in our first step, what we are doing, basically we are going to create a p-type material, and we are also going to create a n-type material separately. Okay, so this is how we are going to create a p-type and n-type material. Next, let us see some step-by-step process to create a p-n junction diode. So to create a p-type and n-type material, silicon or another semiconductor is doped with different impurities. Now only we have seen how we are going to dope our semiconductor material with, to form a p-type and n-type, right? Trivalent atoms like boron are added to create a p-type, while pentavalent atoms like phosphorus are added to create a n-type material. Now only we have seen with an diagrammatical example, right? Now what we are going to do, when a p-type and n-type semiconductors are brought together, a p-n junction forms at the boundary where they meet. The p side has an excess of holes and the n side has an excess of electrons. So what we are basically doing, we are taking a semiconductor bar, and on one side we are going to dope this semiconductor bar with p-type material, and on another side we are going to dope n-type material, and in between a junction is formed which is known as p-n junction. How it is going to form, we will discuss in detail in our next slides. Okay, so what we are going to do, basically we are going to dope one side with p-type and another side side with N type and a PN junction is being formed. Okay, so when a P type and N type semiconductors are brought together, a PN junction forms at the boundary where they meet. The P side has an excess of holes. So here in the case of P type, we have excess number of holes. We have excess number of holes. Whereas in the case of N type, we have excess number of electrons. Excess number of electrons. Okay. Next, how we are going to form the depletion region? So this region, the middle region, is known as depletion region. Okay, so basically electrons from the N region and holes from the P region move across the junction due to the concentration differences. So basically the holes from this particular region are denoted with, holes are denoted by a positive symbol, and electrons are negative, represented by negative symbol. Okay, so this movement of holes from the positive side, from the left side to right side, or the P type to N type, and the movement of electrons from the right to left. Okay, so electrons from N region to P region, N region, and the holes from P region moves across the junction due to the concentration difference. So due to the concentration difference between these two regions, there is movement of holes from the P to N type, and and the electrons from N type to P type. So as this movement happens, what happens? As this movement happens, electrons and holes will recombine at this junction. Okay, so basically at this junction, the recombination of these holes and electrons will happen at this junction. Okay, the holes and electrons will recombine at this junction, and what happens after recombination? They will neutralize each other. Okay, so after recombination, the holes and electrons are going to neutralize each other, which means what is meant by neutralization? Which means a positively charged ion and a negatively charged ion are created at this particular junction. I will draw it here. So these are holes, and we have electrons, moving from P type to N type region due to the concentration difference, and the recombination occurs at this particular junction. At this particular junction, forming, neutralizing each other, and forming positive and negative ions. We have positive ion and negative ion here. So due to the process of recombination of holes and electrons, we are going to form a depletion region is being formed here. Okay, a depletion region will consist of positive ions as well as negative ions. So these positive ions and negative ions are basically neutral. So they have no charge with it. Okay, so these positive ions and negative ions are neutral in charge. So they don't have any charge on it. Okay, so a depletion region has been formed, and this positive ions and negative ions don't carry any charge. Okay, so basically what happens further, it will restrict this movement. So after forming this positive ions and negative ions in this depletion region, so if a hole wants to move further, so if further a hole wants to move across this region, what happens after the forming of depletion region? This positive ion will repel this hole. Okay, so this hole will repel back, and it will not able to cross this junction. As well as in this case also, after forming this depletion region, if further an electron wants to move from N region to P region, it will repel back due to the negative charge, which due to the negative ion, not the negative charge, due to the negative ion which is present. So this electron will repel back, and it cannot cross this junction. So this is the depletion region. So I'm talking about the case where no external voltage is present, and the PN junction diode is in equilibrium state. I'll write it here. So initially the PN junction diode is in equilibrium state. So basically what happens in the equilibrium state, a positive, due to the depletion region which consists of positive ions and negative ions, so these positive ions will repel the positive charges, that is the holes, and these negative charges will repel the electrons, that is the negative charges, and there is no further movement of the ion holes from p type to n type region, and electrons from n type to p type region. That is what it is going to happen. Okay, so after this recombination, so as the electrons and the holes meet near the junction, they recombine, neutralizing each other. So this leaves behind the positively charged ions in the n region and negatively charged ions in the p region junction. So this is what it is happening. Okay, so this is how a depletion region has been formed. Sorry, this is wrong representation. This is, wait a minute. One second. This is the depletion region and these are holes. This is the representation of holes. Negatively charged ions will be formed in the p type, like this. These are holes. Okay. Sorry, these are electrons. So this is p type and this is n type. Okay. So as the electrons and holes meet near the junction, they recombine, neutralizing each other. This leaves behind positively charged ions in the n region and negatively charged ions in the p region near the junction. So this is the junction, depletion region or PN junction. Okay. So ideally, or in the equilibrium case, if we discuss, there is no further movement of electrons from p type. Sorry, there is no further movement of holes from p type to n type, and there is no further movement of electrons from n type to p type. So this is what it is going to happen in the equilibrium state. So in the depletion region, this creates a region with fixed positive and negative ions on the either side of the junction, called the depletion region. So depletion region is nothing but the combination of positive and negative ions on the either side of the junction, and it acts as a barrier. Okay, so the depletion region is acting as a barrier that prevents further movement of majority carriers. So basically in this p type, what are the majority carriers? In the p type, holes are the majority carriers. Okay, in the p type, holes are the majority carriers, and in the n type, electrons are the majority carriers. Okay, so this depletion region will act as a barrier and it will restrict the movement of this majority carriers, that is the electrons from n type to p type and the holes from p type to n type. Okay, holes in the p type and electrons in the n type across the junction. Formation of built-in electric field. So the fixed charges in the depletion region create an electric field that points from the positive ions in the n region towards the negative ions in the p region. Okay, so basically what is happening, due to the formation of this depletion region, an electric field will develop. Okay, an electric field will develop from n region to p region, that is from positive ions to negative ions. So an internal electric field will develop in this direction from n type to p type, that is from positive ions to negative ions. So the fixed charges are nothing but the positive ions and negative ions which are present in the depletion region. Due to this fixed charges, a depletion region is in the depletion region creates an electric field that points from positive ions in n region towards the negative ions in the p region. Okay, so the electric field opposes further diffusion of electrons and holes, preventing more carriers from crossing the junction freely. Okay, so what are all the things which are obstructing our flow? So first one is the positive ions. which are obstructing our, which are repelling our holes not to flow from p type to n type, right? And the negative ions which are restricting the flow of electrons from n type to p type. And due to this positive ions and negative ions which are present in our depletion region, an electric field is formed, right? Now only we have seen. So due to this electric field which is flowing from our n type to p type region, so this field is also further restricting the flow of our holes from p type to n type region, and the electrons from n type to p type region. So this electric field is also restricting the flow of holes from p type to n type region and n type to p type region, right? So this is what it is written here. So the fixed charges in the depletion region creates an electric field. So due to this fixed charges, an electric field is created that points from positive ions in the n region towards the negative ions in the p region. Now only we have seen this. Okay, so this electric field is opposing the further diffusion of electrons and holes, preventing more carriers from crossing the junctions freely. Okay, at the starting of our discussion, we have seen that electrons and holes were freely moving across a junction. That is, the holes from p type to n type and electrons from n type to p type. They were moving freely, right? So after some time, what happened? There was a creation of a junction. Why the junction was created? Due to the recombination of holes and electrons. Okay, due to the recombination of holes and electrons, a junction was created. So due to the creation of junction, in the what actually does the junction consist of? The junction consists of a chargeless ions, that is positive ions and negative ions, which are formed due to the recombination of electrons and holes, right? So they are formed due to that, right? So there are no charge on the depletion region. Okay, so due to that formation of depletion region, there was a restriction of the flow from flow of electrons from n type to p type, and the restriction on the holes from p type to n type. And due to this electric field which was developed by this our ions, positively charged and negatively charged ions, the electric field which is flowing from n type to p type region, due to this electric field also there is a restriction on the flow of this majority charge carriers, which are, that is nothing but holes and electrons. So due to these factors, in the equilibrium state, after certain time, there is no free movement of this majority charge carriers. I am focusing on the term majority charge carriers. Okay, majority charge carriers. Right. Next. And in equilibrium state, we have reached the equilibrium state where a balance is reached between the diffusion carriers and opposing electric field. At this point, the PN junction reaches equilibrium with depletion region, preventing further movement of majority charge carriers across the junction. Just now we have discussed this, right? Next. However, there is a case called minority carriers. Okay. So, however, minority carriers, electrons in the P region and holes in the N region. So, what are the minority carriers in the P region? What are the minority carriers in the P region? Majority are holes, then minority are electrons. Okay. The minority charge carriers, the electrons in the P region, and the minority carriers in the N region. Majority are electrons, so minority are holes. Okay. So due to the movement of minority charge carriers, that is the electrons in the P region and holes in the N region. Okay. So the minority charge carriers, electrons in the P region and holes in N region can still cross the junction under certain conditions. This case we will see later. Okay. So a certain minority carriers will cross the junction. A little amount of minority carriers, not a huge amount of minority carriers, only a little amount of minority carriers will cross the junction. Okay. Which is leading to a small current. Okay. Yeah. Next. So this is about formation of PN junction diode and creation of p-type, n-type and depletion region. I hope it is clear, right? So are you having any doubt or queries up to now? Right. I hope it is clear. What are the characteristics of PN junction diode? So unbiased state. So in unbiased PN junction, no external voltage is applied. That is, in equilibrium state, there is no biasing. So basically, there is a positive bias and negative bias that we will discuss later. So in unbiased state, what is meant by unbiased state? That is, no external voltage is applied to this particular PN junction diode. The depletion region remains its width. So the width of the depletion region remains the same, and only a small amount of current due to the magnetic areas flow across the junction. Okay. So what is meant by unbiased state? So no external voltage is applied to this PN junction diode. Only the PN junction diode is left ideally. Okay. No external voltage has been applied to this PN junction diode. Okay. So this is unbiased state. This is unbiased state. So in this state, the depletion region will maintain its width and only a small amount of current will flow due to the minority carriers only. And what is meant by forward bias? So applying a positive voltage to the P side and negative voltage to the N side reduces the depletion width, allowing current to flow as the barrier is lowered. Okay. So we will see what is meant by forward bias. So this is a forward bias. P type, N type, and a positive voltage if it is applied to the P side and a negative voltage is applied to the N side, it is called a forward bias. Forward bias. And if we apply reverse, that is, a negative voltage is applied to the P side and if a positive voltage is applied to the N side, it is called a reverse bias. It is called a reverse bias. Okay. So I've just introduced you with this basic terms: forward bias, reverse bias, and unbiased. So we will discuss this in more detail with the VI characteristics in our upcoming sessions. Okay. Yeah. So if you are having any doubt, you can ask me. Yeah. So that's all for this session. So if you like this session, please like, share, and subscribe to my YouTube channel, All About VLSI. And if you are having any doubts or queries, please feel free to ask me. I will try to help you. Okay. So that's all for this session. Thank you.